So let's talk about the memory layout of a typical C program. I think before going after what the layout is and what all sections does it have, I think let's shed a bit more light on why it is necessary. Why should we care about how the memory is laid out? How or rather what pieces of our program go where. And the very critical reason is if we know that, we would first of all know like what the boot flow does, or rather boot flow in the sense, if let's say our program is laid out on a layer of OS, what will happen? If our program is running on a bare metal, what will happen? And this is very critical because we want to get as much juice out of uh, the processor as we can in terms of efficiency. And if we know like wherever code, data, everything lies, we would know how to optimize it. And we'll talk about very like niche optimization details later on in this video. But first, let's go about talking on how our code is structured. So I think Piyush, a sample code if you could write, that would really help. And meanwhile, I'll also talk on what all sections exist.
Okay,
So
sure. So what kind of a program would you want me to
I
write?
would want one with local variables, one with globals, globals initialized and globals non-initialized.
Okay, fair.
Perfect. Okay. So basically, we have like four sections to care about in terms of memory layout. One is BSS. Second would be the data section. The third one would be the text section, and the fourth one would be the stack. And now because you are hearing stack, you'd also think of heap. But in typical embedded program, what happens is you generally don't rely on dynamic allocation because the behavior of dynamic allocation is unpredictable. Let's say if you have a code which is which is running in a very limited resource, which is typically the case with embedded systems. What would happen is uh, if you allow dynamic memory allocation there, you might run into a situation where the heap is sort of running out of memory, and you might run into very weird scenarios which puts the system in jeopardy. So in order to avoid it, what programmers typically do is pre-calculate how much memory their program is going to need. And it's fairly easy to do. You have some tools which are part of GCC tools and available to do that. And once you know what is the maximum amount of memory your program is going to use, you pre-allocate it in the RAM itself, so you never are bothered about dynamically getting the memory, and hence you don't need the heap. And the another advantage with this is, because you don't never are going to need the heap, you can remove that dynamic memory allocation code or the heap management library from your glibc and save space there. So I hope that was clear. And yeah,
Right.
so that Piyush, can you also make a list of the four sections?
Okay, sure. Let me then write it here. So you hinted at the dot data section, the dot BSS section, then we had the dot text section, and which one was that?
And then stack.
Okay. So then we had the stack.
So it's perfect. So okay, so here Piyush has on the left hand side a typical body of a program, and it has like two globals as I can see. One is initialized, the other one is not. So X being 11 is the initialized global, right? Y is non-initialized. So the C standard suggests that any non-initialized globals are default initialized to 0. Right? So there is a key here, key distinction here, and this is what we'll talk about. Just bear with me. And then you have a function body where you have two variables again. One is initialized and one is not. The initialized one being A and the non-initialized one being the variable B. All right. Now,
by the way, I should just call out that I am completely aware of the fact that we are returning A plus B and B is not initialized. We are aware of that.
Yeah.
Go ahead.
Perfect. So, okay, let's think of your code executing the first line inside the main function, which is initializing A to 10. Now, before that, very first line of your code being executed, we as programmers take some things for granted. Like there are certain assumptions we go on with while writing the code. The first assumption being that, hey, if I were to access x at any point within my main, I should get the value 11, right? So if you print x, you should get value 11. It should be magically done. I am not doing it in my code, but I expect that value in x to be 11. Okay, that is the first observation we have made. All right. And
Being
11.
right. So I'll just read, right, because I was also writing. So you're saying that at any point within the main program, if you chose to use or print x, what you're suggesting is that the answer would be printed as 11. The value would be available as 11. Okay.
Right.
Go ahead.
So now let's ask ourselves this question as to who does that? Who initializes the x memory location to 11? Because our code is not doing that.
Okay.
Right?
So let me then write it here. Who initialized x?
X. Perfect.
Right.
And second question is, where is this 11 being stored? Because someone has to know that x is being initialized to 11. Let's assume that someone is doing that. In if your code is running in user space, that most likely would be the role of OS. But then OS has to know that what value x needs to be initialized with. So there are two questions here. Now, the answer to the first question is like two-parted. First, if you are running on top of an OS, which is user space code, which generally, in typical embedded systems or firmware, that would not happen. But
right. So, Mohammed, let me pause you here. And recently, kind of, I read it in this C standard, which is, so if the C code is running on an OS environment, it is called the hosted environment.
Oh, nice. Hosted. Yeah, that's a very good terminology.
Correct. And I felt that it was very fitting to introduce that right now. Okay, so this is, whoa, what is that? Give me a moment. Dealing with hand-eye coordination. Okay, so one is the hosted environment, and the bare metal environment is called the freestanding environment.
I was not aware of this, but that makes a lot of sense.
Yeah. So what I want our viewers to know is that in a hosted environment, your binary, the compiled code is absorbed or kind of loaded by the operating system. So I'll just say loads it, like OS loads it. And in case of a freestanding program, there are hardware programmers. So these are like actual hardware devices to which you provide your binary, and they will put it in the memory of your target. So that's the difference. And okay, back to you, Mohammed. So you were talking about who initializes the value of x to 11 in hosted environment and in the freestanding environment. And then we also did you introduce as to where the
no, I think I'm correct. So I'm now supposed to deal to the second question, which was, where does this 11 data come from? So in both the environments now, it is clear who loads it. One, OS, and then secondly, a hardware programmer, where it could be Piyush, would I be right to say a hardware programmer could just very well be a NAND flasher who flashes into a non-volatile device, something like that? Okay. So now this second question, where is 11? How does they know where, what data to load, right? And that is precisely why we have the data section. So the 11 would somehow the linker. I don't want to introduce too many terms just yet, but know this, that when you compile your C code, it gets structured into these four sections, right? And 11 goes and takes the place in data section. Now, and the standard definition of what will go inside the data section would be all the initialized globals or your static variables within the body of a function.
Right. So let me actually write that
Right.
down. So what goes in the data section? You said initialized globals, and the second one is statics from. Uh, let me just write it this way: initialized static from functions.
Yes.
All right.
Perfect. So if you had, let's say, if you can scroll a little bit up, Piyush, yeah. If you had in your main body, if you had, static int m, let's say, or any other
So
variable,
static
yeah,
int m equals to
equals some
100, let's say.
value, yeah. Then even this 100, I'm not saying
Hmm.
the variable m, that would
Right.
the space for that would be devised later, but the value 100 would be going under the data section.
Data section. Fair. So then what I'll do here is, so it would look something like so,
Hmm.
roughly speaking.
Roughly speaking. And guys, also, one thing to clarify, we are aware that in standard terms there is another section added called RO data, and we are
Hmm.
sort of omitting it out just because it will make the sort of conversation more complex, and I think it's not relevant to at least get us started with a C memory
Hmm.
layer.
Hmm. Hmm.
So RO data
It,
is, you can imagine, it would be a subset of your data section.
right. So you have the data section, and
Hmm.
then some part of it
Hmm.
would be covered as RO data.
Hmm.
And the idea is, well, Mohammed, now that we are at this
Hmm.
point, let's also talk about just briefly RO data. And
Hmm.
so what people can imagine is right now, 11, both like x and
Hmm.
m here, both of them are integers, and
Hmm.
these can be modified.
Right.
Right? So the problem is twofold. One is it needs to be initialized. So 11 and 100 needs to exist somewhere for the loader or like the booter program to initialize these memory locations.
Hmm.
That is number one. But the second one is, had we had a const,
Yes.
right? So then the thing is, it's a variable which we should kind of not write to. So the writes should be discouraged. And how do you do that? By making it read only. So
Hmm.
by placing it into the RO data section. So ensuring that RO data kind of is either guarded by the operating system
Hmm.
against writes, or in a freestanding environment, it goes in a memory that's ROM like,
Right. Right. Perfect.
where the writes are not.
Hmm. Hmm.
Okay, so we are not covering RO data just for that reason, that it's simply this choice of, okay, we don't want this variable to be modified, so let's just make it const. And once you make something const, it's a
Hmm.
candidate that you can put in
Hmm.
RO data.
And
Okay,
we promise, we'll revisit RO data when we talk about how do we guard this, right? So
yes,
we have a typical hardware which does this performing, which
right.
does this sort of bookkeeping of what sections are given what permissions, and when we
Right.
talk about that, the peripheral is called MMU and MPU, the
Mm,
combination of both.
mm,
We'll revisit
mm.
the RO data, is we'll promise you that. Yeah.
Right. When we talk about like the OS environment and the hardware, this is a good topic to revisit then.
Yeah.
Okay, cool. Go
Perfect.
ahead, Mohammed. So you
So
were talking
coming,
about
hmm,
11 and
11,
uh,
yeah. So now when so to drive this point home, we have like our entire code. When we compile it, the compiler and linker both know what to keep where, and 11 and 100, which we saw above, would be placed in data section. And
mm,
when in both the cases of hosted environment or the free standing environment, that data section would be somehow interpreted and loaded into the correct memory. So
yes.
that's what my uh,
Hmm,
key takeaway for data section would be. Now
right.
let's again, sorry Piyush, I'm making you
So
scroll.
I just that's okay. Mohammed, do you mind if I just very quickly? I don't know if our audience will want it, but I just
No, go
wanted
ahead, go
to
ahead.
kind of mention that GCC, the compile. You mentioned that the compiler will take in our C program,
Hmm.
the C files, and then at some point during the linking phase, what it will do is it will create this layout of different sections. So there would be dot data section, dot whatever BSS section, dot text section. So the linking or the linking phase or the linker is the one which kind of creates this layout and puts different things in different places. And I just want to hint our audience right now, which is linker does that by following something called the linker script. This again, we'll come to this much later, but there is always a linker script involved. Even if the user doesn't provide, it uses the one that comes with GCC. So just like a random plug to reorient ourselves. And okay, go ahead, Momita.
Yeah.
You were talking about.
Yeah. So I think data section now hopefully should be pretty clear. What does it contain and what is the role of it? Okay. And now if you can scroll a little bit up, Piyush, to the code. Let's focus on the int y, which is not initialized. And you would say, hey, why not put it into the data section itself and mark it as 0, which is completely fair. That is how I suppose the very early stages of a program might have looked like. But now think of it, in a typical code, there are most of the variables which you don't need to initialize to any value to begin with. It can just as well be a 0, right? Okay. So now if we put those collection of variables in a different section, what we can do, and that section is called BSS, by the way. It stands for block started by a symbol, and that means that symbol is 0. Okay. So let's say you have like collection of, and I would urge the audience to look at a typical code base, an embedded code base. You will see a lot of global sprinkled everywhere, and I would say almost I don't want to give a number of percentages because that can vary, but most of them would not be initialized. So there is a heap of heap, again, not confused, there is a bunch of variables which are not initialized to anything. So those are, yeah. And if we put them in a different section altogether, what we can now do is we don't have to consume the memory in the data section with this bunch of zeros. I hope I'm able to drive the point home. Piyush, you can add your thoughts later.
Right. Okay. So one thing that I think we'll come to in a bit, but I want to go back to the data section and introduce a new reality, which is new reality or a new perspective, and that hopefully kind of will and not ensure, but will kind of enable our audience to understand the importance of BSS section. So one of the things we talked about was, okay, in the data section, so this is the data section, we have this value of 10, later 100, and all of that is fixed. Fixed meaning it is at this location. In a freestanding environment, so you have like a microcontroller with in the memory you have these values, and obviously the microcontroller can be power cycled. Power cycled meaning it can be restarted. So you have a microcontroller. Again, I must repeat and reiterate that we are discussing about the data section for a little bit so that we can understand the BSS section a little more. Fair? That is where we are at. And what I'm proposing is we have this microcontroller, which freestanding environment, which had internally ROM and RAM. So non-volatile memory and volatile memory. Right? So the code should go and be placed in the ROM because every time you power cycle a microcontroller, you don't want the code to be lost. Mohammed, you're on the same page with
yes,
so far?
yes.
Okay, great. So I'm choosing to explain it to you, hoping that our audience will catch on. So the code should stay in the ROM because every time we power cycle, so to speak, reset the microcontroller, the code should not vanish. Okay, now the question to ask is, if the code doesn't vanish, that is great, that is expected. But then what happens to these values? Should they vanish? These are, let's say, the main function we wrote is the starting function. So as soon as your microcontroller starts, well, all of a sudden you're using values of X and Y, let's assume. But now the X value
is
should be
lost.
still available.
So yeah.
Right? So question then is, how do you ensure that these values are retained? Because you want the initialization data to be available. So what happens is, we put the data section in two places. Okay, this is going to be interesting now, and I want our learners to pay very careful, like very close attention to what's coming. So in the ROM, we put the data section and, well, the code section, which will come to, or the text section. So every time we power cycle our microcontroller now, we are assured that the data values of 0 and 100 are retained. They are not lost. Number one. The second thing is, we talked about int x being, let's say, 10.
Piyush, can you write a little bit to your...
Thank you. Yes. So, so we are talking about int x being equal to 10. Right? And we said that this 10 was stored here, and then I reasoned that this 10 will go and sit in the data section in the ROM.
Yeah, some persistent storage, which lets us not discard or not lose the important info which is needed to run our program, basically.
On a power cycle.
On a power cycle.
And by the way, how did all of this come here in the first place? Well, hardware program. We use the hardware programmer to dump our code onto the on the ROM, and once that was done, we said that our microcontroller can be reset, power cycle. And now I reasoned that the data section will live in the ROM. Right? Okay. But the second problem now is, so the value of x, this 10, resides here, which is great. But what if my program wanted to do x equals to 20 at some point? Now all of a sudden, this 10 value cannot be modified, right, because it is in the ROM. So what ends up happening is, we have RAM, and during the boot up of the microcontroller, there will be some piece of code that copies over the value of the data section from ROM to RAM. So this 10 appears, this 100 appears here. Pay very close attention. This happens, this always happens, even on the operating system it happens. Power cycling makes the case very clear as to why one should do this. So what happens is, during the start of your program, as you're, before actually starting to execute things, there would be some piece of code that transfers over the entire data section from ROM to RAM. Right? So far, if people are with me, the other trick that's used, and that happens in the linker script world, what we say is, hey, when you are generating the binary, use the load addresses of the ROM. But in the code, when we are doing modification of this value x, the address of x should be from the RAM. So now what happens is, when we are modifying x, it is getting modified here, and the code is using this location, and then we reset the microcontroller. What will happen is, again, next time it is booting, this section is again copied from here to here, and 10 and 100 were the values which were the initialization values, they were available. Okay. Now coming to the answer of BSS, what happens is, it's literally a waste of space.
Yes.
If we keep the BSS section here and then have all zeros scattered here. What makes sense is, we just remember that we want to initialize the BSS section in the RAM. And why in the RAM? Because we are going to modify those variables. The uninitialized global variables will also get a value. For example, y was uninitialized, but later we might set y to 100 or 101. Where does this modification happen? Well, it happens somewhere here. But here's the neat part. If we had copied over, we were having a construct like this in the ROM, by the way. So we had the 10, 100, the data section being saved. And then we also decided to save the BSS section with all zeros. And what if we had MBs of that? Or, well, KBs of that? Then we have KBs worth of zeros, which is based of ROM space. You could have had KBs worth of text section or code section. So what we tend to do is, we just remember, okay, how much space is the BSS occupying? And then what we do as part of, again, that initialization code is when we copy over the data section to the RAM, what we go ahead and do is say, okay, now this BSS section, we can just write zeros there as part of the software. And that is why saving the space and the fact that the zero initialization can be done by the software, that is one reason why we do not save those values in the
Right. And I think that is the reason why we have split our data section into two. One being the uninitialized data, which is like itself the data section, and the second one being the non-initialized globals, which are in the BSS.
Correct.
Yeah.
Okay, go
Perfect. I
ahead.
think I completely understood it, and I hope our audience would also have understood it.
So then, can I go ahead and just summarize?
Summarize. Yeah, I think that would really help.
Fair. We did not talk about the .text section. Do you want to talk
Right.
on that?
I think let's summarize BSS
Oh,
and data first, because both are highly related.
fair. So then, what BSS and data are in context of global variables? The initialized global variables, the initialization value goes in the data section, dedicated section which holds those values, and then the BSS section. Well, we just have to remember the start and end of it. And
And
again, how one remembers is linked scripts and initialization code. There is a way to do that. And then there is text section.
which we'll talk about. Yeah.
Yes. And
Piyush, sorry, just to drive this point home, you have, I think, very well mentioned the comparison of ROM and RAM. So can it would really help me per se if there is a table called ROM and RAM, and see sections are present in both or one or where. I think that
fair.
would
Oh,
really
oh,
drive the point home.
right. So let's draw that again. So let me draw two memories here. So one being the ROM, the other one being the RAM. Fair. So in the first off, what people need to remember is the data section will exist in two places, both in RAM and in ROM. The load address is generated for the ROM. So let me just say this is called the load address. So Mohammed, do you mind muting yourself just for
Oh,
a bit?
sorry.
There
Yeah,
is some
sorry.
background noise.
Yeah.
Okay. Just unmute yourself once maybe I'm losing track or something like that. So load address is generated for the ROM region, and during the binary generation, the compilation phase, well, the values are put here, and that is always true. Okay, the ROM region will not have a BSS. That doesn't have BSS. What it has is it has text section, the code. Right? So the code goes here, and there will be some part of the code, the initialization part, which will say, hey, take the data section from the load addresses and load it into something called, or transfer it into something called the logical addresses. So the RAM region is called the logical address region, and the ROM region is the load address region. So the data section will then be copied over from the ROM to the RAM by some part of code, right? Load region to logical region. The code also makes reference to the global initialized variables with their logical addresses. So there will be, you can imagine, two places that X exists. One is in the ROM and other was in the RAM. But the code will always use the address that is pointing to the RAM, the logical address. Okay, so if that much is understood, so data section exists here. The BSS section only exists in the RAM. And what happens is there is some other part of code which remembers or which understands where this BSS section in the logical address space, which is the RAM region, where it starts and for how many bytes it extends. And what it will do is it will end up initializing it with some value. The C standard tells us that it has to be the value of 0, But if you really want to be evil, then in a microcontroller environment, you can set this to, all Fs or some weird value and mess with everybody else's life. Because they'll assume that the global uninitialized is having a value of 0, except it's having a value of F. Anyways, so all zeros here. And the text section always lives in the ROM or the read-only memory. And again, on an operating system, everything here is loaded into your DRAM. But then there is a certain readable, writable section that is available, wherein the data and the BSS will be made available. Okay, so the code always is in the read-only section, and the BSS doesn't exist on the ROM side, only exists on the RAM side, and it's put there, or the initialization is done by some startup code. Okay, so Mohammed, this is what I had to mention about this.
Perfect. I think this really makes things clear, especially the distinction, and I hope the noise is not
No, it's no
interrupting.
longer.
Yeah. So the distinction really makes the things pretty clear as to why the the things are designed in certain way. Why do we divide things into certain sections and all.
Hmm.
Uh,
Okay,
I think
then just
in the next one we can talk about the text and the stack sections a little
sure.
bit.
Yes, so let's do that. I'll then let's then conclude this lecture, and then in the next one let's hop into the stack and the text section.
Yeah.